Hey everyone, I'm going to wrap up the notes section on divergence. We ended class going over an example that used this fact right here. So this is something important to know, something that I think can and will be useful for us. So if we have FA vector fields on R3 and P, Q, and R have continuous second order partial derivatives, then we know that the divergence of the curl of F is equal to 0. Again, I want to mention, other notations that might be helpful to you, but that is something good to know. Commit that one to memory, might be helpful. Okay, quick concept check. If you have not thought about these yet, I would probably write down your guesses and then come back and check when you're done if you got things. So you're basically saying, are we vector fields? Are we scalar fields, or are they meaningless? So again, I would pause before I start going just to see if you got it. But here I go. So B, we'll be taking the curl of a vector field. And we can take curls of vector fields is what we want to do. So this answer right here would be a vector field. For C, the divergence of F. That would be the divergence of a scalar. But remember that the divergence is the dot product of the gradient operator and vector field. We can't do that. So C is meaningless. The curl of the gradient, the divergence of the curl of the gradient of F. What is gradient of F? Gradient of F is a vector field. So this would be divergence of, so the curl of a vector field is a vector field. So this would be divergence of a vector field. So this would be a scalar field. So the divergence output is a scalar. All right, next what do we have? We have our vector gradient of F crossed with curl of F, which is another vector. A vector cross another vector is going to give us a vector. So we have our vector field. And then we have gradient of F cross divergence of F. So this would be a vector cross a scalar, which you should know we're not allowed to do. This quantity is meaningless. So in class, we talked about what curl looks like, in quotations right there. Now let's talk about what divergence looks like. So if F, our vector field, is the velocity of a fluid or gas, then the divergence represents the net rate of change with respect to time of the mass of fluid or gas flowing from our point per unit. So just note that some of these explanations are very specific in what we are describing. So if we're talking about a vector field being the velocity of a fluid, then our divergence is going to be the net rate of change of the mass of the fluid flowing from that point that we're looking at per unit. In other words, the divergence is going to measure the tendency of a fluid to diverge from the point. It is spreading out and measures flow in versus flow out. It is the spreading out and measures flow in versus flow out. If divergence is less than 0 at a point, then mass is accumulating in a spot and is compressing, gaining there. In other words, it's not diverging or leaving. Flow in is greater than flow out. We call this a sink. That point, maybe I should say. The point is a sink. If the divergence of F is greater than 0 at a point, then mass is flowing out. In other words, it's diverging or leaving. Flow out is greater than flow in. At that point, we say it is a source. So we have sinks and sources. If divergence of F equals 0, then F is said to be incompressible. Incompressible. Remember, with curl equaling 0, we called that irrotational. I think I spelled that rotation. Oh my gosh. Irrotational. And if divergence is 0, we say F is incompressible. Okay. Let's think about your bank account for a moment. Give you the idea of whether you are a sink or a source of money. If money tends to accumulate in your bank account more than it leaves, the divergence, we would say, is negative. Flow in is greater than flow out. However, if money tends to be leaving your bank account more than it comes into your account, the divergence, we would say, is positive. That flow out is greater than the flow in. We definitely want our bank accounts to be sinks, folks. If money tends to be leaving your bank account and coming in at the same rate, the divergence would be 0. All right, let's look at our visual examples. Each vector field F represents the velocity field of a fluid. Only the part of F in the xy plane is shown. The vector field looks the same in all horizontal planes because F is independent of Z, and the Z component is 0. At each point, determine if divergence of F is negative, positive, or 0. You know what? I probably should mention this in class a little bit more deeper. F is independent of Z. So that means you can look at this picture and create like stacks. You can stack them up, stack them down. They all look the same. It doesn't matter what Z value we're calculating it at. They all look the same if you take your like cross sections of any plane parallel to the XY plane. So how do we do this? For curl, we had to look at the vectors around the points. We had to look at their magnitudes. We had to look how many there were. We're trying to look maybe if there was a little, I'm sorry, I'm blanking here. Symmetry. Oh my gosh, sorry about that. A little symmetry to anything around the points. This is kind of similar. If we're going to take a look at P1 first on our example for A, I'm going to draw a little circle around here. And we need to think about this. So look at the vectors going in. So I'm kind of looking there, I'm kind of looking there. When you compare some of these vectors to some of these vectors, what can we see? I'm feeling like when I am looking at this, I am seeing that those vectors flowing in look longer than those flowing out. So to me, it looks like there is at point 1 more flow in than out. So that would tell me the divergence of F at P1 is not equal, I'm sorry, less than 0, because then it would be negative. It looks like a sink. It is not a source to me. For P2, let's do something similar. If you think you got the idea, pause, take a guess, look at it, say it in your mind before I get there. I've done enough talking where you might already be able to have looked at it and already decided, and you're wanting me to get on with it. So I'm looking at these vectors over here, comparing them to these vectors over here. I think this is a little bit clearer in my opinion. It certainly looks like we have maybe more vectors, or at minimum, larger vectors, magnitudes bigger, for those that are leaving, that are going away from our point. So because it looks like there, to me, is more flow out than in, I am going with that the divergence of F at P2 is greater than 0. That is a source. It is sending stuff out. All right. As for curl, I don't know. Some of these I'm feeling for point 2, if we wanted to talk curl, maybe there's some rotation in a clockwise sense. Maybe these look a little bit larger than those. Kind of hard to tell. Kind of looking at the other ones over here. I don't know if I have a good idea of curl for that one. I'd have to come back and think about it. But we're not talking about curl, we're talking about divergence. So look at B. See if you can guess what the divergence at point P would be. Again, pause, think about it for a moment if you want. I'm going to go start writing the answer. If I take a circle around there, we think about the vectors coming in versus the vectors leaving. And what do we notice about them? It's like the same amount. The vectors entering look almost identical to the vectors leaving. So don't confuse this with the idea of curl, because we talked about this. This one is easier to tell. I can see that rotation would be induced in a clockwise direction for curl. So I know this would have a curl that is non-zero right there for sure. But our divergence of our new f at this point P, to me, because it looks like flow in, looks like it equals flow out to me, we would say that is 0. Things look like they have the same length, looks about the same amount, kind of looks symmetric coming in and going out. So I'm going with 0 for that one. I hope you have a wonderful rest of your Friday. Enjoy your weekend, do some homework, and I will see you on Monday.